LLM memory breaks when old facts overwrite new ones. Use Graphiti in Python to store relationships with time, provenance, and change history. This is the pattern you'll be able to implement by the end, which captures evolving relationships and resolves the current project with provenance. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Memory in LLM assistance often fails because facts change and the model forgets the timeline. Graphiti's temporal knowledge graph memory records facts together with when they were true and where they came from. That makes it easy to ask, what should the assistant have known on this date? And to point back to the original episode that created that knowledge. Teams use this when preferences shift, project requirements change, or system state evolves. The payoff is fewer hallucinations, clearer provenance, and the ability to answer date-specific questions. The core idea is straightforward. Store episodes as time-stamped records. Extract entities and relationships from each episode. Link those nodes so versions and sources are preserved. Then query the graph with a reference time. The graph returns the state that was true at that moment, a timeline of belief rather than a single brittle snapshot. It's great for clarity and provenance. The trade-off is you need a bit more plumbing than a plain vector store. We will build a tiny example that shows an onboarding fact, a conflicting update, and then two time-sliced queries that return different evidence. You will see how to initialize a Graphiti client, add episodes with reference dates, query the graph at 2 points in time, and assemble a prompt that contains the recent episodes and provenance. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now let us create the client and prime the graph indices. This snippet sets up a Graphiti client connected to a FalkorDB-backed memory graph and primes structural indices. We import asyncio and Graphiti, then create an async setup function that instantiates Graphiti with a multi-tenant graph name, so later snippets reuse the same client. Inside the coroutine, we immediately call build indices and constraints, which generates the indexes and unique constraints Graphiti relies on for temporal episode upserts and fast retrieval. Returning the configured client lets us stash it in a module-level variable for reuse. The printed memory-ready value confirms the active graph namespace. The key takeaways are that the client is async-friendly, the indices are required for episode upserts, and the graph namespace makes tests repeatable. Next, we will write a first episode to seed the timeline and record provenance. This example stores the first user preference episode, so Graphiti can start tracking temporal change. We reuse the shared client and call add episode through asyncio.run, supplying a descriptive name, the text payload, and a reference time that pins the fact to January 3rd, 2025. Episode type.text instructs Graphiti to treat the body as natural language, letting its extraction pipeline create nodes and edges when LLM-powered enrichers are configured. Persisting the onboarding source helps provenance and evaluation traces downstream. The print statement echoes the recorded episode tag, confirming the inaugural memory fact was captured. In short, this step turns a single user statement into a durable, time-anchored memory. Now imagine the user changes their mind, and we need to append the update and compare snapshots. This code appends a conflicting preference update and runs two time-sliced Graphiti searches to illustrate temporal recall. Inside scenario, we add the February 17, 2025 episode, again flagging episode type text so the engine can revise relationships. We then await asyncio.gather, over 2 search coroutines, each using reference time to ask what the assistant would have believed on January 10th versus February 20th. Wrapping the results in len star produces deterministic integers, even if the underlying search result structure changes. The printed theme snapshot past and now values show distinct payload sizes, signaling that the graph returned different evidence for each snapshot. This demonstrates temporal branching and how later episodes overwrite or augment prior facts, depending on the query date. With episodes added, we can inspect the entity graph directly to see what nodes exist for a person or concept. This snippet inspects the entity graph by pulling the top-ranked node summary for Riley from Graphiti. The entity snapshot coroutine issues retrieve nodes with a text query and limits results to 1, letting Graphiti fuse embedding, keyword, and graph signals for ranking. We convert the first node search result to a short string slice, so the tutorial stays agnostic to the exact data class fields, while still showing what was returned. If no node matches, the helper defaults to the explicit no match literal, making failures easy to spot. The printed entity snapshot snippet confirms that Riley now has a graph entry enriched by earlier episodes. This step helps you validate the graph structure and the entity extraction pipeline. Finally, we assemble a retrieval payload for an LLM prompt using the most recent episodes about the topic. This example assembles a retrieval payload by harvesting the most recent Graphiti episodes about Riley's UI preferences. Within assemble prompt, we call retrieve episodes with a focused query, so the engine returns temporally aware conversation fragments alongside their provenance. We flatten each episode search result into a trim string and join them with new lines, pairing the summary with a lightweight question that an orchestrator could hand to an LLM. Keeping the context under control makes it easier to tune prompt budgets, while still citing the original episodes. The printed context prompt preview shows the stitch timeline that will seed the assistant's response. This gives a neat handoff from memory to generative model. Graphiti gives you a dated timeline of belief, episodes with time and source you can query later. Use this when facts change often or when provenance matters. Run the indices and lifecycle code up front. That setup is the one caveat you'll need to manage. Next step, scale this small timeline by adding more episodes and measuring retrieval accuracy over a larger set. Try increasing episode frequency. Then add an ANN index or timing checks to see how retrieval latency and relevance change. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.